Well, good morning. This is 8:34. Sorry, I'm 4 minutes late getting started, but I tried to run down the hall one more time before 8:30, and I ran into somebody. I had to tell them about my computer problems. So a little bit late getting started. But now we're here. I'm here anyway. This is differential equations, and right now I'm the only one in the classroom. So I'm going to get started from where we left off. And then we will go from there. Hopefully some students will be coming in. All right. I would ask if there are any questions, but just remembered something. Hold on, I'm going to pause. Okay, now we're back. Do have a student in here now, so we were on page 26, section 1.3, chapter 1, Introduction to Differential Equations, 1.3, Differential Equations as Mathematical Models. And before we get started, any questions? No. Okay, good deal. So here is series circuits, and you said you didn't need to take E&M, right? Electricity, magnetism, and physics?
I don't have to take physics.
Huh?
I don't have to
take physics too. Well, you're going to have to take it here. Okay, no. This is series circuit. Consider a single loop LRC series circuit shown in a figure here. There it is. And I will actually draw that for you here, and I'll try to get it done similarly to what they do. Okay. This is they call it capital E of T. Now, that's from an old reference here, and we seem to be, this is the strangest projection. Sometimes it stays over there, sometimes it comes over here. I'm going to go on and erase this because the other reason, if I don't, you see what happens? It's really hard to erase as it dries onto the board. So if she needs this later, she'll have to rewrite it. Okay.
Yeah, she used red last time.
What's that?
The red stain.
Yeah, and I've got to get this. Is that bothering to you? I've got some Windex back there. I can clean it up. What's that?
I ain't OCD or anything.
Okay. Oh, really? Oh, no, I'm just kidding. Okay. All right. This is from the old name. We used to call it EMF. Because that came from electromotive force. But the voltage is not a force. So they quit calling it electromotive force, but still called it EMF. So now they still call it E of T. Now, when I see in physics E of T, I think energy. This is not energy. It's similar, but not quite. This is voltage. So I wish they'd have said V of T, but the book is calling it E of T. It doesn't matter what you call it. Potato, it doesn't matter. All right, now this is sending a circuit in a series circuit through an inductor, and that has the symbol L. Okay, and then it goes down into a resistor, and that's the symbol R, and then it goes over to a capacitor, and that's the symbol C. Okay? Now, we call that an LRC circuit, okay, for inductor, resistor, and capacitor. Now, the reason you don't see a battery symbol here, this doesn't work. You don't have LRC circuits on DC circuitry. It can't happen, okay? It's only on AC circuits. So this is that way. Sometimes you'll see that represented without a letter, as if you care, as this. And that generally means it's going as a generator, is producing this, not a battery, which has cells. And the other thing you can think of, that could be representing a sine wave, which indicates voltage is a varying voltage, alternating current. Okay. So anyway, you don't care about any of that anyway. Okay, so yes?
Yeah, question. Are you familiar with circuits at all?
Somewhat, yeah.
You ever seen like a circuit where it's like drawn, it's drawn kind of like a U?
Yeah.
And like you have like your power source right here.
Yeah.
You have your positive or whatever, I don't know what we used to call it. And then you go like down here, and then you have like your light bulb or
right.
Your receptacle.
Resistor? Oh.
Your
your outlet, yeah.
Then your outlet, and then you got to wire it back to negative.
Uh-huh.
Is that like the same process as that?
Okay. Yeah, if you're talking about household circuitry, yeah, it's this kind. It's AC, it's not DC. Computer is DC, but I'm plugged into the wall. How can that be DC? Because this little black box here. This is they call it an adapter. Yeah, AC adapter. It adapts the alternating current to DC because all your computer stuff, your cell phones, everything else run on DC. Okay?
And that's AC?
Well, the plug is, yeah, the wall is always AC.
So our TVs run on AC?
Yeah, right. Anything that doesn't have a black box, or doesn't have to be black. You know your phone, this is a pencil sharpener, it's not one, but you know there's an adapter you plug into the wall and you plug your phone in.
Yeah.
The little, okay, that's an AC adapter, okay, because that's changing the AC from the wall to DC because your phone is DC. Anything that has a battery associated with it has to be DC. This computer has a battery, it's DC. The phone has a battery, it's DC.
Are you familiar with the Xbox?
It's what?
Are you familiar with the Xbox?
Say that one more time.
Xbox?
Xbox? Oh, Xbox. Yeah, right. I know what it is, but no, I'm not familiar with it.
Its power cord has a big brick on it.
Okay, that's probably...
And it's like, it's got a motor in it, but, you know, you said it's got a battery, the Xbox don't have a battery.
Okay, you sure? Okay, well...
It might have a battery, I don't know. It's just,
yeah, I know.
It's got a big fat brick with it, though, you know what I'm talking about? Like the black box.
Yeah. Well, yeah, I don't know what's in that. It could be or not. But yeah, Xbox is a box. And I know sort of what you're talking about. A Roku is a box that you have to go through. Now, I would say those are still AC. Those box contains all the electronics that are going to be doing whatever they're doing. And Xbox has to be really doing.
It's got some kind of motor in it.
Yeah.
It's loud, it's like...
Yeah. Oh, that's because it's about to explode. No, I'm just kidding. Okay. They are doing all sorts of things because that's where you play video games and all this kind of stuff, right?
Yes, sir.
I'm a dinosaur. I don't know what the current things are, but yeah, that is the driver for all that. So yeah, you need a box for that. Like Roku is doing all sorts of things with signals and things like that. So I doubt if that's an adapter. That's the actual guts of the thing. You know, sort of like the main board of your computer, except this is at DC. You know, you have to go in through the motherboard and stuff like this to do the things you're doing. Okay. All right. Your automobile got a battery. DC.
It's DC.
It's DC. Everything on your car is DC. One exception. Your engine is turning you don't have a Prius, do you? Or
no.
Yeah. Okay. That wouldn't apply. But if you have a gasoline-powered engine, okay, then you have a generator there to recharge the battery.
Alternator. Right?
Yes, but the generator, yeah. And the reason for that name, it's actually a generator, but it generates AC, alternating current. So the alternator also takes that and converts it to DC, so it can charge the battery. Otherwise, on the up cycle, it would be charging the battery, down cycle, discharging. It would never charge the battery. So what it has is usually I think nowadays they call it a dual diode or something like that flips this side of the sine wave. As soon as it starts to go negative, it flips it up so you have a pulse DC. It's always positive, and it's recharging the battery that way.
It's weird.
Yeah. In the old days, it was a split ring commutator, and you have split ring, and as soon as the thing went halfway around, then the nodes would flip, and then whereas this side would be positive, that side negative, and the thing would be turning around like this, and as soon as it flipped to here, then this side becomes positive and that side becomes negative, so it kept it. That was a mechanical way. The dual diodes. A diode only allows electricity in one direction and not the other. So you have one that when the generator is going this way, it feeds it through this one. When it goes to negative. This one blocks. This one allows it to go this way. So again, you have a pulsed DC circuit, so you can recharge.
So the AC is the sine wave, and the DC
AC.
is the cosine wave?
No. Cosine also goes negative.
Oh.
The DC and when you're converting like this, your alternating current is like this. So it does, whatever device you're using, flips the negative here, so it then goes like that. So it's always positive. So it's direct current, meaning it only flows in one direction, but it's pulsed, because it's sometimes higher, sometimes low. A battery is a flat line, okay? It's always the same.
That's what's called direct.
Yeah, direct, yeah, going one way, exactly. Alternating, so. Okay, there's your physics course, and no extra charge, okay. So let's erase this. I don't think it's necessary for what we're going to be doing, so let's get back to this. Okay, so there's your circuit. It contains the inductor L. Why do they get L? I don't know, so they probably use I for current, okay? Resistor R, that makes sense. Capacitor C for a capacitor. The current in the circuit, after the switch is closed, and I didn't draw a switch on it, but they didn't either, but when it closed, the current is denoted by I of T. Okay, so I'm going to show it going in this direction, but you know alternating current goes in both directions, but this is your current as a function of time. Okay, and it's also following a sine wave, because this is an alternating circuit, or cosine wave, either one you want to call it. Okay, the charge on the capacitor at any time t is denoted by Q of t. So this is a current. The charge is Q as a function of t. Now, a little bit of more physics. I is always dq dt. Current is the time rate of change of charge. Okay? As the charge is varying, so is the current. Okay? As the current varies, so is the charge. So the charge here. But a capacitor builds up charge. Okay? And nothing, see there's a gap there. Nothing goes across here. So it builds up charge for half a cycle, and then builds it on this side, and then builds it on this side. Actually, there's two charges, positive and negative, so these are constantly alternating, okay? See, that's why it wouldn't work in a DC circuit, because all the charge would build up here, positive charge build up here, negative charge here, it would stop. Okay, nothing, no other charge would flow. But because this is alternating current, you have charge building, changing, so it's completely fluctuating. Okay. Now, those fluorescent lights up there, have you ever been into a light fixture?
No, but I know they explode.
Yeah, okay. The thing that usually will explode in it is your capacitor. Okay. That's what builds up, because you see you have an enormous amount of charge or voltage built up in there on a capacitor to give it a lot of energy. A capacitor is an energy storing device. Okay, it stores the energy that's applied here.
Even when it's disconnected?
It can. Okay, if I were to unplug this, there's our capacitors in there too. If I were to unplug this, not with it on, but when I'm shut down, I unplug it, my power light stays on for just a little second and then fades out. That's because the capacitor is discharging. Okay, so it won't say keep it forever, but it does, the computer is still drawing a little bit, so it takes a little bit, and then finally the light goes out. Because the capacitor discharges, okay, because it's building up that. But because you see the energy required to send they're mostly electrons going down the tube at really high rates of speed, what is happening, have you ever seen a tube that's broken and that white powder inside?
Yeah, the white powder?
Yeah. That white powder is called a phosphorescent material, meaning that when electrical energy goes by, that material the electron jumps up an energy level. Okay? Okay? And then when it leaves, it falls back down.
And it glows.
And then it glows, exactly.
We
And
learned
that's
that,
what gives the light.
we learned that in biology, like certain like sea animals.
Yes, exactly.
And the bottom, like
Phosphorescent. Yeah, exactly.
you have like an electron, it goes up, and then when it goes back down, like
It gives off a photon of light.
Yeah.
Exactly. And that's quantum mechanics, quantum physics. That light comes in quanta, or packets of energy, and that's when it falls from one level to another level. And the phosphorescent material, the way they build it and stuff, they can make soft white, bright white, whatever, but that's what's creating light from there. So you're not heating up a filament, so therefore fluorescent tubes are a lot more energy efficient.
Fluorine in it, right?
Say again?
That powder is fluorine and phosphorus?
Well, it's called a phosphorescent material. That doesn't mean it has any phosphorus in it. It may, but it's phosphorescent. Basically means it gives off a phosphor, which is the old name for ephemeral fluid. So it's giving off light.
But I just didn't know what's in them. What makes them glow.
Okay.
It's like the fluorine.
Okay. I don't know. I don't know what the chemical is.
They get called like fluorescent.
Fluorescent.
Oh, yeah.
Yeah, fluorescent. Yeah. Yeah. And perhaps that's because it has fluorine, or I don't know. I do know that, especially the older bulbs, the vapor that is flying up and down the tubes and by the way, it's not a gas, it's an ionized gas, meaning it's gained or lost electrons. I don't know which, maybe both. And it's a mercury vapor. The old ones were. I don't know if the new ones are. And that's why some of them, they didn't want you putting them in landfills because they're afraid that trace amount of mercury could leach into the drinking water and stuff like that. But people do put them in landfills. So, and that's the downside of fluorescent lighting, is that the materials are somewhat hazardous, both to work with and to store and leach out and all that kind of stuff. That's why nowadays people are going. I hope they're going to the LEDs.
Mm-hmm. LEDs are taking over.
Yeah, and they should be, because they're even more energy efficient than those, and
they don't use tungsten either, right?
No. I want to say there's no heat involved. You see, a tungsten filament, what you're doing, you're heating it high enough until it glows, and that's what gives you the light. Well, most of the energy is spent heating the thing, not producing light. And that's why the bulb gets really hot if it's been on for very long, okay? These don't get nearly as hot. They do get hot, but they don't get nearly that hot. And the LEDs also don't get as hot. I think these are LED projectors, and I feel almost a little bit of heat coming out of that. And there's a fan here, and that's very little heat coming out of that. Oh, here's one. That's the intake. This is the outtake. A little bit of heat.
It's not that bad.
Not that bad.
But I got LED light bulbs, and
right.
After about 3 hours, because you know how your room gets hot because the lights get
right.
Not that bad.
Yeah, exactly. And probably if you went to unscrew the light bulb when it had been on 3 hours, I don't know how. Huh?
It won't burn your hand.
It won't burn your hand. Incandescent. Yeah, that burns. Okay.
The good thing about LEDs too is the tungsten material. It's a rare earth.
Right, exactly.
It's only in China.
Okay. Well, the Chinese are controlling the market. I bet you they're harvesting it in the Congo. I don't know that for a fact, but you see, the Congo has Democratic Republic of Congo is one of the richest mineral countries in the world. It's one of the poorest countries in the world because they've been ripped off first by the colonizers and then by the economic colonizers, which are the Chinese. We probably have tried really hard too, but the Chinese they're controlling the market on rare earths.
So if we got LEDs, we don't need that rare earth.
Right. Well, I don't know what they make LEDs out of, but it could be something else. You know what LED stands for?
Yes.
The L is?
L is that L? Light?
Light. Light emitting diode, just like I just said, the diode. Okay? And that's what's happening with that. And I actually think this goes back to, I may be wrong on this, something I'm pretty sure that Newton discovered, but it may have been after Newton. It's called the photoelectric effect. I don't know if you've run into that in your studies, that when you have electricity, certain materials give off light. But now, they didn't know photons of light. That was not what they were talking about. They just meant light. Photo means light. Photography is capturing light. I'm sorry, we're getting off on all sorts of things here. But the LEDs, they've had them for decades. But see, the first LED they were able to commercially produce, I may have it wrong, but I believe it was the red one. It only gave off red light. Okay? And then, not too many years or decades later, they came up with a green one. Okay? So that made good Christmas lights, okay? But that's about all, okay? But they couldn't make a commercial light out of that because red and green do not make white. It sounds bizarre, but it's true. Finally, I think a guy in Japan, but I think also he had worked in the U.S. and probably collaborated with a U.S. physicist, came up with a blue one. That's fairly recent, like in the last decade, you know. And when that came out, now you can put a combination of those three to get enough of the visible spectrum. See, blue is an actual color, and red is an actual color on my spectrum, but the green is a combination of other colors. Okay, so you get enough of those together, and you can produce white light. So once they had the blue, they could do an LED bulb, and that's what they've done. And the cost is coming down now. They at first were very expensive, but now they're coming down. But again, I don't know what materials go in doing those LEDs, the light emitting diodes.
I've noticed like everything's going LED now.
Yeah.
Like houses, like car lights are brighter than ever.
Oh yeah, yeah.
But I hate that blue crap. You know, when you're going on the highway and it's dark and something got some blue lights that are like 10,000. It feels like a light bar being shot at you.
Yeah, well, the thing is, that's not, it may be an LED light, but it's one that's not been, they did that for a purpose, and I don't know what the purpose was, but you can adjust the voltages on that. If you go to Home Depot or Lowe's or somewhere like that, look at your LEDs, they have soft white, bright white, all sorts of LED shades. All they do is adjust which diode gets a little more juice than the other, It's all done electronically. So they didn't have to. They intentionally did that. And there was some reason. I think they were trying to get all the cars to do that. And, of course, they did. You promised you wouldn't be here today. We were looking forward to your not being here. And here you show up anyway. Okay?
Work I do, I can't work when it's raining. So.
Oh, I see. Okay. We'll pray for rain on Thursdays. Okay. No, I'm just kidding.
Shoot, we need the rain.
Yeah, I know. We really do. Who cares about your bills? We want you in class, okay? We want you paying these bills, okay?
Already done that.
Yeah, okay, well, see, we're happy then. Yeah, who cares about the rest? Okay, no, I'm just kidding. All right, we're talking about LRC circuits roundaboutly. But anyway, I just gave you one formula here. Current is the time rate of change of charge. The capacitor depends on charge buildup. Current is the time rate of change of charge. Okay? So let's continue. Now, according to Kirchhoff's second law, I was thinking this was the first law, but anyway, let's see. No, it is. It's called the loop law. The impressed voltage, E of t, is equal to, on a closed loop, must equal the sum of the voltage drops. You see, this is providing voltage. And by the way, do you know what voltage is?
It's V, or like what voltage is with the formula.
Okay, I know what formula you're going to give me, probably Ohm's law, right?
I think it's Ohm's law. It's like the V omega. It's like V equals omega over resistor.
Omega is resistance, so yeah. Okay. What you're doing is Ohm's law is E is equal to IR. I is current, R is resistance. It's amp time omega. Yeah. So yeah, that's what you're getting. But I would say, what is actually voltage? Voltage is energy per unit charge. That's what you're providing here. That's in direct currents with the battery or in alternating currents with the generator. You're providing energy to the charges. Okay? So you're giving the charges the energies here. The charges are moving around in the current here, and then they're going through the devices, and the devices are using that energy. Like the energy of the on the electrons or whatever that are charging the capacitors, getting through the light, that's using the charge. The power, which is the generating plant, wherever it's coming from, is giving the energy to those charges. The light fixture, the computer, whatever, is using the energy. The inductor using the energy, the resistor using the energy, and the capacitors using the energy. So this is the energy source. Those are the energy sinks. They're using it. Okay? Now, so according to Kirchhoff's second law, the voltage supplied, which is energy per unit charge, the voltage supplied by the generator, that's up in voltage from minus to plus, that's equal to, and it's alternating, so that really makes no sense, but the energy being given here is some of it's being lost here, some of it's being lost here, some of it's being lost here. The total of the loss has to equal the total of gain. It's a closed loop. It's a closed loop. So that's Kirchhoff's second law. Okay? Now, the impressed voltage, or EFT, on the closed loop must equal the sum of the voltage drops of the three or however many inductors, capacitors, and resistors you have. Since the current I of t is related to charge by, as I just wrote, I of t is equal to dq dt, okay? Here are the other relationships, okay? And these are talking about the voltages. The voltage, and I want to say, I'm going to give it the symbol V. I don't think they do here. I'm going to say V of t here. This is similar to E of t, same thing, but that's for your supply. This is for your use. The V of t is equal to the inductance L times your rate of change of your current. But because current is the rate of change of charge, that's L d2q dt squared, okay? It's sort of like velocities and accelerations, okay? A velocity is the time rate of change of displacement. Acceleration is the time rate of change of velocity, but because velocity is this, it's the second time rate of change of displacement. So it's similar here, okay? So that's your energy drop across an inductor. The energy drop across the resistor is just I times R, and that was Ohm's law. Voltage equal current times resistor. They use a little I here most of the time. For direct currents, they use capital I most of the time. But because I is dq dt, this is also R times dq dt. Okay? And then the capacitor, strange formula here, and by the way, this is the voltage drop. I'm going to put voltage drop across the inductor, voltage drop across the resistor, and then the voltage drop across the capacitor, strangely, is 1 over C times Q. Okay? No derivative involved with that. Okay? So if this E of t is equal to L d2, second derivative of Q with respect to t, plus R times the first derivative of Q with respect to t, plus 1 over, or Q over C. Okay? That is now a differential equation. Okay? So let me write it down. I like to do the E of t first. They do it second. It doesn't matter. E of t is equal to L d2q dt squared plus R dq dt plus q over c, or 1 over c times q. Okay? So you see, here's your the independent variable here is q. No, dependent variable is q. Independent variable is time. And this is also a function of time. So, and that's why they wrote it the other way, because most of the time we write our differential equations with the derivatives on this side and the function on the other side. That's why they wrote it that way. I just thought this worked better physically. Okay. This is a parameter of the system, the strength of your inductor, that's the strength of your resistor, and this is the strength of your capacitor. So this gives you your differential equation, second order, linear differential equation, and this is your EOT, which goes on that side. Okay? So there's another example. Shortest one in the book, and the one I took the most time on, of a series circuit. Alternating series circuit does not work for the other. The inductance L is measured in henries, and I'm really surprised they put that as a little h. That really should be a capital H because it's named after a guy whose last name was Henry. Okay? So this is a math book, not a physics book. Okay, your resistor is named after Georg Ohm, but they use an omega. I wonder why. Why didn't they use a capital O? It's fancier? Well, maybe. But let's say, give me a value of a resistor. Just make up a number. 4. So let's say we had 4 ohms of resistance.
40.
Oh, yeah, that's why we can't use a capital O, because it looks like a 0, and that would be confusing. So when something is confusing, they usually go to the Greek alphabet. In the Greek alphabet, they have the letter corresponding to O in the...
Omega.
No, it isn't. It's Omicron. But that's that. That wouldn't work. But see, the Greek alphabet actually has 2 O letters. Omicron follows nu, which is, that's like lambda, mu, nu, Omicron, go on. But omega also starts with O, but that's at the end of the alphabet. So for omega. But they capitalize it. That's a capital omega. That's not the lowercase omega. You know what the lowercase omega is? Looks like a W. You've seen it before. That's the lowercase omega. But because it's named after someone, they use the capital. Okay? Now,
they don't capitalize the Henry?
Yeah, but this book doesn't. Physicists do.
Okay.
Bad. Okay. All right. But you have to capitalize that because that's what everybody knows. Now, physicists are a little nuts, though. Remember that. Okay? There is another concept in physics. This is resistance, which is a resistance to a flow of current. Okay? There is another concept, which is conductance, which is the ease with which charge flows, which is just a reciprocal of your resistance. Okay? But they needed a name for that. And nobody really, one person discovered it, I don't think. People had been using it, but it needed a name, and they didn't know what to name it. And by the way, an ohm is, Georg Ohm is spelled O-H, that's his name. So what did they needed a unit to call conductance as opposed to resistance. What name could they use for that? They didn't name it after anybody, so they needed a word to name the unit. What unit could they use? Well, they came up with one. They came up with a mho. Isn't that logical? Doesn't that make perfect sense? To a physicist, it does.
It's just ohm backward.
That's ohm backward, exactly. Since it's reciprocal of resistance, why don't we just spell ohm backward? And that's exactly where they got it. Okay? Now, what symbol will you give a mode? We've already used M for meters and capital M for mega for a prefix. We've used M's to death. So what can we use as our symbol for a mode?
MHO.
A what?
I don't know. MHO.
Oh my God! Yes, exactly. It's not a letter in anybody's alphabet because it's reciprocal. They just inverted the omega. Okay, way more than you called for today, right? Okay, but this is true. I'm not making this up. Physicists are sort of nuts. Okay, all right. I'm a physicist. Okay, never mind. Okay, so, all right. Any questions on Kirchhoff's law? Series circuits for the, oh, and by the way, I wanted to say this too. Capacitance was named after, the unit is a farad, named after Michael Faraday, a very famous British physicist who did a lot of the work with it. So that should be a capital F too. The book makes it a little f. Shame on them. Okay? It should be capital F. And by the way, the capital H for Henry, which is what the inductance was, that's why, because Henry came along and entitled that first, or they named after him first, or whatever, because later when, goodness, I can't remember his first name, Heinrich Hertz came along with frequency. They wanted to name the Hertz after him, and they couldn't use capital H because Henry was already was capital H. So that's why Hertz are now HZ. Most of the other things are single letter. Hertz is HZ because they already had capital H for Henry. So, more than you ever called for here. Okay. Let's move on to the next application of differential equation in mathematical models. And this will be one we're a lot more familiar with, falling bodies. Okay, and again we go back to good old Isaac Newton, his first law of motion, second law of motion. We won't use the third here, but basically what you get out of this, now this isn't exactly how Newton probably described it, but it's what we use today, is that his second law of motion says the mass of a body times the acceleration, which is d2s dt squared, time rate of change of displacement, second derivative, okay, is equal to minus mg. For a falling body, the acceleration on it is the acceleration due to gravity. So this is your formula there. So again, you have a differential equation, and because you have mass on both sides, you can eliminate the m, and there's your differential equation. d2s dt squared is equal to minus g. Now that's a falling body if you're ignoring air resistance. Now if you have air resistance in the picture, and we'll get to that next time, I'll hold off on that one. Okay? Now, that's a second order linear differential equation, ordinary differential equation. That is a constant there, so you'll need two initial conditions. Usually you know your displacement at time 0, and that would be some, they call it S sub 0, yeah. But you also need a second because it's second order, and that's usually the velocity. S prime of 0 is usually called the initial velocity. If you know those two, then you can solve that system of equations. And it's pretty straightforward, and it's the textbook solution. And here's what it turns out being, and you'll see it in most physics texts. And if you've had Physics 1 already, you said, both of you? Yeah. Hopefully you remember this, otherwise you will change that grade to an F, is minus 1/2 gt squared plus v0t plus S0. There's your standard solution for that differential, that initial value problem where you know the two initial values. This is the solution. whatever your initial displacement is, that's got to be there, because when t is equal to 0, that's your displacement. T of 0 is equal to S0. And if your first derivative, if your t equals 0, your velocity, initial velocity is that. Again, t is, well, then you have to take the derivative of this. This disappears. This would be minus gt plus v0, and that's equal to 0. That goes away, and you just have 0. So, works out perfectly. Okay. Now, as I said, this is good for air resistance equals 0, which seldom do you run into that. On the surface of Earth, never do you run into that. Now, if the velocity is low enough velocity, it's negligible. But if things are going at a very rapid pace, like a jet airplane, even your car going down the road at 60 miles per hour, I think you probably, I don't know if you did it. I know I did it as a kid. I like to stick my hand out the window. Back then we didn't have air-conditioned cars. Other people did, but we didn't. We were too poor. Okay? Yes. And then do it like this, and yeah, exactly. And then feel that. And if you're going along slowly, that felt good, Going along fast, and this is almost pull it. Yes, exactly. So at a higher speed, you have more air resistance. So you are weird kids, weren't you? Okay, never mind. Okay. It was just fun to do, wasn't it? Okay. So there always is air resistance, except there was one experiment that was done with absolutely no air resistance. A falling body. Okay? Know where that was done? Surface of the moon. The astronauts did that. And I mean, it really does work. He held a heavy hammer in one hand and a feather in the other hand. Dropped at the same time. Both hit the surface at the same time. Does that happen on Earth? No, that feather does this. The hammer goes down. That's because this needs more air resistance and has a lot less mass. So the heavy hammer, that little bit of air resistance doesn't change its fall at all. The light feather, it reaches what we call its terminal velocity very quickly, and it takes a long time to go down. Okay, so the astronauts did a physics experiment. They've done many, but they did that one. Very simple one. Okay, and they caught it on tape too. Okay, before the famous experiment by Italian mathematician and physicist Galilei, he was doing must not have, Okay. Anyway, he preceded Newton by just about one lifetime. The very year, if you notice here, the year that Galileo died, 1642, the next year Newton was born. Really bizarre. Sort of like they did a tag team, on the way up and out, or something. I'm making that up. Okay, you watch too much wrestling. Okay, but anyway, Newton built on Galileo's work, especially for his first law of motion. Then he went further and carried the second law. But anyway, he's mentioned. And by the way, any of these names that show up, they could be paper topics. Hint, get your papers written, people. Okay. That was a paid advertisement. Okay. The resistive force was ignored in the falling body that we did before. Here we have to not ignore it. Okay. So here and they go through all the equations. I'll get right to the differential equation. And this is more closely to what probably Newton did than what mass times acceleration. He talked in terms of momentum. And this would have been his equation, I think. I don't know. I don't read Latin, so I don't know how he did it. dv dt, that's the same as this. All right, because v is equal to ds dt, so that's the same on the left-hand side, and that's equal to, now, they've changed your signs around here, and I apologize for that. mg, here they were making that negative, here it's making positive, because we're talking about falling bodies going down. We were up there too, but they made the g negative. Now they're acting like downward is the positive direction, minus kV. Okay, so that is when you take into air resistance. This is the proportionality constant to deal with air resistance. The air resistance is a function of velocity. The faster something moves, the more air resistance it moves. So that's why we cage this in terms of velocities. And we're taking downward velocity being positive, that's why we changed the sign here. So acceleration would be positive, and this is a force upward that is resisting fall downward. Okay? So this is a resistive force. Since it is, they made that negative and this positive. So sort of a turnaround from there. I think they were being fairly sloppy. Okay? Now, another way you could express that is go back up here. That's m, and again they've reversed direction on it. d2s dt squared is equal to mg minus k times ds dt. Okay? Now, rearrange that, not too subtly, m d2s dt squared plus k ds dt is equal to mg. And that's the other reason they change the sign so everything can be positive. Other things, they'd all be negative, and then you change the sign anyway. Okay, but this is now your differential equation. Linear, second order differential equation, independent variable S, independent variable T, dependent variable S. Okay, so there's your differential equation there. All right, suspended cables. Boy, that's kind of a messy one. Okay, I know you're going into bioengineering, biomedical engineering, right? Or just biosystems engineering. Okay, you're going into mechanical, not electrical, mechanical. Okay, you could run into suspended cables. Civils would certainly run into that, but you could. How are we doing?
Cables that deal with bridges.
Yeah.
Bridge structural.
Yeah.
So bridge support.
Yes, exactly. Yeah. So, yeah, you probably deal with that. It's very much a mechanical problem. It's also the electricians deal with it in their
the power lines.
Power lines,
Those
yeah.
or figuring out how much, what kind of material to use, how much weight they can sustain.
Exactly. So that's all these are suspended cables. And they have this illustration in the book. I just about assume not. You don't have a book, though, do you? Okay, I'll go on and draw it as best I can. It's going to be pretty bad. Okay, here's your XY plane here. Okay. X being here and Y being here. Okay. And here's your suspended cable, where there's a bridge, telephone wire, whatever it happens to be, and this should be symmetric on either side. And what they're going to talk about, this is the wire, whatever that cable is, okay? Let's talk about a point here, P1, and some other point up here, P2. And these could be anywhere within the domain of that wire, okay? Well, down here, by choosing this one at the minimum, you know the tension in the wire here, and I think they call this T1, and this is a vector, by the way. You don't have to. They put it bold in the book, and that's why you don't notice it. Now, for this segment between there, you can represent the weight as capital W. Now, again, this is a math book, not a physics book. Capital W in physics would be work, and it wouldn't be a vector quantity. Work is always a scalar quantity. This is weight, which in physics you'd usually use a little w or something, but the book is using capital W. Okay? And then up here, your tension is this way. Your first derivative, your tangent line. And that's your T2 at that point. And that's also a vector. But this has a component downward and a component horizontally, vertical and horizontal. Well, this is T2, I want to call it H, and this is T2V. That should be a subscript V, so it's not as confusing. Okay, you don't think it's velocity or something. That just means the vertical component of that tension. Okay. Now, this component certainly is related to and would be, for this to be in equilibrium mode, static situation here, those would have to be the same. These would have to be the same too, but just in opposite directions, okay? So that's basically your setup here, okay? Now, this is your angle theta here, okay, between the horizontal. So this T2 vertical is going to be the magnitude of T2 times the sine of theta, because that's the opposite side. This T2 horizontal, and these are actually components, so I guess I don't need to put the symbol. These are the components of the vectors in the I and j direction, so you don't need the arrow over them. And this would be T2 times the cosine of theta. Okay? Now, if you're just taking magnitude of them, these two have to be equal, so this is equal to T1, and this one is equal to the weight. So this is equal to the weight. And again, we're just going to do magnitudes here. The weight is T2 sine theta, and the T1 is T2 cosine theta. Now, what if we divide those two equations, which seems like a rather bizarre thing to do? We eliminate the T2s, okay? If you divide this, this over that, then the T2s go out, okay? And I've got them backwards or upside down because this, of course, I said those backwards. Yuck! You let me get away with that? Okay? This is your W and that's your T1. Sorry. No wonder things were looking backwards. The horizontal is T1 and the vertical is the W. Okay. Woo. Okay. And if you did the ratio of those two, you get here you get the tangent vector, which your tangent vector is your first derivative, dy dx, and that's equal to W over T1, and that's where they get that formula there. So again, a linear first order differential equation. You would need one initial condition to solve it completely, but we're not getting into that now. So that's the ratio of the weight of the segment of the wire to the tension in the horizontal direction. This way. Okay. Now, the rest of this is a lot of blah, 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 as if this hasn't been so far. It basically is going into what direction we're heading. For most of the rest of this course, maybe all of it, we're going to be doing an analytical approach. We're going to be trying to, so far, they say, here's a differential equation. This happens to be a solution to it. Verify that. That's what we've been doing all along. So, to me, that's just sort of backwards. Why don't you show us how to get that solution rather than tell us this is a solution? Now you tell me that whether it's right or not, okay? So we're going to be doing it analytically for the next several chapters, probably the rest of the course. If we have time, okay, then there's also a qualitative analysis, and that's basically saying, well, is this the only solution? Are these the only solutions? You know, are there any other solutions? Then you're doing sort of qualitative. We've done a little bit of that so far. And then the third kind is, what if that differential equation we can't solve? There's just no way. It's too complicated. Well, then basically, and this is what most people use these days, whether they realize it or not, is numerical analysis. And that's when you use a computerized program to do your differentiation.
Like Maple software?
Probably it doesn't. I'm almost certain it does. Are you familiar with Maple?
No, it had it at UAB.
Yeah.
Actually, that's how they differential equations. The whole course is on the computer. They have a lab.
Is that right?
Yeah, it's all. They got a lot of Apple desktops in the lab, and they use Maple software. That's the class.
Okay.
Yeah, that's the class.
So you don't do any analytical solutions?
No, I don't think so.
Oh, wow.
It's just called a theoretical approach.
Yeah.
And that's it.
Yeah. Well, that's reality.
Yeah,
we're dinosaurs. We're still doing the analytical approach. Okay.
That's the class in the computer lab.
Yeah.
For like an hour and a half.
Yeah.
2 days out of the week. You
Yeah.
got a whole floor for that.
Yeah. So, but you have to know what you're supposed to be putting together with those things. All right. They have some remarks here. A dynamical system is one that you do have varying with time. Okay. And the time-dependent variables are called the state variables. The state of any system, that would be pick some point in time and that might be your initial conditions. But then you can have changes to that. It's a dynamical system. So what if you do put something else in the circuit here? How does that change your system? That's the response of the system to an impulse. I'm not going to go into all this. You can read that on your own. These, to me, just seem like they tie you up. Now, I've already given most of these, and I don't know if there are answers in the back or not, but if you want to look through them and think through them, if the answers are back there, population dynamics, 1 and 3, I assigned those last time. Newton's law of cooling and warming was number 5. Spread of disease or technology, meaning disease in a technology, but also, okay, that's number 7. Mixture problems, either 9 or 11. If those are in the back, you can do those. Draining a tank, that was Torricelli's law. That was 13. Series circuit, we stopped before this last time, so this is 15. Falling bodies and air resistance, that's 17. And Newton's second law and Archimedes' principle, which we did not cover in class, but they cover it here. That's, well, they don't have but one even problem for that. So you can read through that, and I would suggest you do it, because Archimedes' principle would be a potential paper topic. Either who was Archimedes, or what was his principle, who uses it, how does it, lots of possibilities there. Newton's second law and Hooke's law, we did do that one, number 19. Newton's second law with variable mass, we did not do that, but that would be like launching a rocket. As you're burning fuel, it's losing mass. So not only is it, most of the time we treat mass as if it's a constant, but not if you're losing mass with burning fuel. So that would be a reasonable one to look at, number 21. Newton's second law and universal law of gravitation. Don't know that we did that one, but if you want to try following up there, that's number 23. And then they have additional mathematical models. You can look at any of those if you want to. You're going into biosystems engineering. I don't know if you'll get into things like studying the uses of a drug in a body. In other words, take an ibuprofen, your blood levels goes up, then over time it goes down. It's a differential equation. You're probably looking just at the systems, right? Okay. Would that be how to control MRIs and things like that? Is that biosystems engineering? Don't know yet. Okay. All right. So anyway, but there are some things here.
What I'm gonna be doing is like treat watershed properties and stuff like that.
Doing what?
Solving like watershed properties and stuff like that.
Really? That's called biosystems? Environmental, okay, got it. Okay, sorry about that. Okay. Yeah, that could be interesting too. I don't see any of these examples that would apply to it, but they could. There's a tactics problem. And then I know the discussion problems are not in the back, but you still could look through them and just think through them and see what other forms these equations could take on. Okay. If you haven't had enough problems so far, there are some Chapter 1 in review. Again, the odd number answers are in the back, or at least some of them are. So any of these odd numbers you can certainly do. Number 1, 3, 5, any of the odds 7 through 11, 13, 15, 17 through 21, 23 or 25, 27 or 29, 31 or 33, 35 or 37, and possibly 39, if you just needed more to do. Okay, so let's leave that alone, and since I did have a little time at the beginning of class when nobody was in the room, I was able to get your test run off, and here is the first test. Okay? Single page, only 9 questions, but you'll find some of the questions have multiple parts, and all of the questions have lots to do with them. Okay? Now, the first one is just taking a derivative. Hopefully that's reminiscent of good old Cal 1. Okay? The second one says compute y prime and y double prime. Again, just Cal 1. Okay? But then combine those as a linear second-order differential equation that is free of the symbols C1 and C2. Now, we actually did some of that early on. We may not have called it doing that, but we did. So there's the first two, find the first derivative, second derivative. And the third was, remember, we called that what? The general solution, I think, the capital F, where you write that down as some combination of F of y, y prime, and y double prime, and you don't have any C1s and C2s now. So work on that. Now, almost certainly, you're going to need some more paper than this. Now, you certainly can use the back if you want to, but I think you'll need more than that. So please turn in all your work, because especially this first test, most of the issues here are how you got your answer, not what answer did you get. Now, taking derivatives, you can just write those in if you can do those. And in fact, that number 2, the second part of number 2, the F, capital F of that, you can just write that one in. But it's probably going to be helpful to show your work. Number 3, actually, it's not nearly as hard as probably you're going to try to make it, but that's something you can basically just write down an answer for that too. But when you get to numbers like 4, and 6 and 7, 8, when it says verify, that's not just writing an answer down, because that would be writing down your problem.
Is that when you get 0 equals to 0 to verify?
Okay, well, sort of. Basically, what that means is, it's what we did, okay? Number 6, well, here's number 4. Let's do number 4. Verify this one-parameter system. There is your solution. Verify that is indeed the solves that differential equation. In other words, you take the first derivative, and then you have to do a lot of manipulation to get it to show that. That's your manipulation. And what you have to show is that this is equal to that. Well, you can just write that down and say, yeah, I verified it. No, I have to see how you verified it. Because the answer is going to be that this is equal to that. But you start with this, and you have to show me how you start with this and get to that. That's what it means verify. So I need to see the steps. by all means, pull out another piece of paper. You can use the back, but I think you'll need more than the back. Use whatever, but turn in all your work. Okay? Because you can't write down an answer here. You can't write down that verification right here, but you can write down what you got for it. Okay? Or at least get it started and then point me to the back or point me to page 2 or whatever. Okay? So especially 4, 6, 7, 8. Anytime it says verify, I have to see the process. And really, just about all this, it's going to be beneficial to you if you show me all your work. Okay? The reason for that is, there's a couple of reasons. One, I've been getting some flack from other instructors that don't like me giving take-home tests. But to do this in class, hey, not even these long summer classes probably couldn't do this. So I want you to work through this. So show me how you got your answer.
You get partial credit if we
I do. That's the second reason that I want you to show me the work. If you do get wrong answers, at least I can see if you were doing the right thing, and I do give partial credit like crazy. Okay, that's why. If all I had was an answer, it's right or wrong. Okay, so please show me your work. Okay. In fact, I almost require it. In my calculus classes, I actually tell them now, if you don't show me the work, you can't get more than half credit for it. Right? So let me go on and say it here. Show me the work on all these. Some of it won't be much. You just take a derivative. Okay. But show me that you've done it. Okay. Okay. So show me the work. Otherwise, maximum I can give you is half credit, even for a right answer. A wrong answer with no work, not going to be much credit at all. So show me your work. I can give you a lot more credit. Okay. So, any questions? Now, I've given it to you today. This is Thursday. Technically, it's due next Thursday. Okay? In reality, you can use more time if you need it. Technically, next Thursday, that gives 2 reasons for that. Number one, next Tuesday, you can ask me questions if there's something you really don't understand about this. Okay? What are you asking for? What? Yeah, that kind of stuff. Or I think you got a misprint here or something like that. Okay. The second reason is you got a weekend to work on it. Okay? Because this is going to take more than an hour. Okay? I promise you that. Okay. So, now, if you need more time, fine. But, I'll phrase it this way. I don't want you still having this test out when I give you the test on Chapter 2. Okay? I do not want that, because you could be way off here, and then you did Chapter 2, and you continue being way off, and I'm grading the same errors over and over. I don't want to do that. I want you to get your errors corrected, so I don't have to grade them over and over again. I'm lazy, okay? I want you to benefit from learning. Okay. Let's see. We only have, about an hour left? Do you need a bladder break? Could you use one? Okay. Since we're stopping at the end of one chapter, beginning of the other, let's go. I'm sorry, I've run off at the mouth. Wait. And let's erase that ink. All right. So, first order differential equations, Chapter 2. You thought we would start solving equations? I thought so too, until you read the first topic, 2.1, solution curves without a solution. Oh boy, that sounds good, doesn't it? Okay? So what we're really going to talk about here is more esoteric stuff. Okay? It'll be 2.2 before we finally start solving equations. So let's try to get through this I don't know if I can do it quickly, but let's get through it so we can finally start solving. Okay. 2.1.1 is dealing with this thing called direction fields. Now this makes sense when you're dealing with first order differential equations. First order only. Okay? And we talked about when your function that you're dealing with in your differential equation satisfies certain continuity conditions, and the partial derivative of that function, even though we're only doing ordinary differential equation, satisfies certain continuity conditions, then you have the existence and uniqueness of solutions, okay? Now, here's what we're going to be considering. What in the world do we mean by an ordinary differential equation such as this? dy dx is equal to f of xy, okay? Remember, that's the one of the forms. I can't remember what form they call this. They have these names for them, okay? And basically, you need to know your interval of definition, that kind of stuff. But what does that really stand for? Sort of step back from the trees and look at the whole woods here. If you had that in a Cal 1 class, what would you think of that? Now, in Cal 1 class, you didn't have two variable functions over here, so. But what does that represent? Second? As a derivative, and what does your first derivative represent for you? Slope of a tangent line. Doesn't it? Isn't that what your first derivative was? Slope of a tangent line. Was it? Oh, man. Okay. We don't only change your physics grade, we're going to change your Cal 1 grade. Okay. So long ago. Okay. You must have had a really lousy instructor, did you? Never mind. We won't go into that, will we? Okay. I was afraid of that. Okay. Now, well, think of this. dy is sort of shorthand when you're talking about incremental, but what was the bigger picture here? We call that, the dy comes from delta y over delta x. That's what the d stands for. And what's the change of y over change of x? Rise over run.
Rise over run.
Which is?
Slope.
Slope. Yeah, this is a slope of a tangent line. If the slope of a secant line for deltas here, tangent line when that delta has become a d, incremental, infinitesimally small. Okay? So, if you know this function, f of xy, they've given it to you, then that means you can draw a graph here. Okay? This is your x, this is your y. And if you know that, you can plug in for any, and you have tick marks here, right? In fact, wait, let me do something dumb here. Let's go back to.
Wait, is that why the y is on top of the dy is on top of the dx because of rise over run?
Okay, say that one more time.
Is the dy is the dy the numerator because it's rise over run?
Y is rise, run is x.
Yeah, that's what I was asking. Is that why we keep doing dy over dx?
Yeah. Except it could be dy dt, dx dt, it could be anything, whatever your horizontal axis is, that's your run, vertical axis. Your dependent variable is always vertical, independent variable is always horizontal. So you're saying, what's the change of this when this changes? That's exactly what you're saying, and that's why it's a derivative. Why can't I get this to, oh, here we go. I could have just done it back. Okay, yeah. Let me use this, okay? I need to change my color again, okay? I'm a chameleon, okay? dy dx is equal to f of xy, okay? Now, if you know what dy dx is at some value x and y, or you know the f of xy, pick an x and a y, okay? If you know that at point 2, 3, when you put whatever this function is, you put a 2 in for x and a 3 in for y, and do this function on it, you can get an answer, right? That's some function of x and y. Plug in a 2 for x, a 3 for y. That's going to give you the slope at that point. So whatever that is, they say here, what if that slope was 1.2? Well, then you make this slope a little bit greater than 1. There's a direction your function must be taking there. Okay? That is the slope or the rate function. Okay? Now, the curve could have been doing like this. It could have been doing like this. It could have been doing anything. We don't know. But at that one point, that's the slope.
Why is it
1.2? They just gave it to us. Okay. If you plug in, you have some function f of y, f of x, y. You know, 3xy plus 2y. Okay. Plug in an x, plug in 2 for x, 3 for y. Now that one probably won't give you 1.2, but when you plugged it in, you evaluate it, you get a number. That's your slope at that point. That's what your derivative tells you. First derivative tells you the slope at a point. Okay? So, the value f of xy for the function of sine blah, 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 a little line segment called a lineal element. Hey. Okay.
Be clear with you.
Wait just a second. I don't know what you're at. All right. If you had all these things filled in for every grid point here, you had a slope, whatever that slope was, you know, then you would have, it would sort of be like what they call a streamline. You would see where things were going if they were going, okay? So that's called a direction field or a slope field, okay? And I'm not about to write all these down. You don't have a book yet either, do you? Okay. I don't know if you can see it from where you're sitting, but let's get over here. This book's a lot easier than my calculus book to do, okay? You'll see here, every one of the slopes has been put in. This is slightly negative here. That looks just about horizontal there. Slightly positive, getting more positive as you go. You know, every one of these grid marks has a little arrow on it, a lineal, whatever they call that before. And you can then pick one and then just follow the arrows pretty much and get a pretty good idea of where it's going. This one looks like it's going like this. Down here, it seems like it's going down here, and then slowly goes back up. These are potential solution curves, right? Now, you may not be right on the money, but you're in the general ballpark, okay? Remember what this section is named? Solution curves without a solution, okay? Now, if in addition to having all these curves here, I mean, all these little arrows here that you can kind of connect the dots, kind of, what if you had an initial position and said, oh, but we know that at 2, 3, the value of this function is thus and so. Then you, at 2, 3, pick the curve that goes through the point 2, 3, and that's the curve you'll use. Okay? So that's kind of what we're doing here. Okay? Now, let's do as well as we can the next one. Okay? So let me clear that. How are we doing on time? Okay, we got 30. Huh?
10:10. You said how are we doing on time? It's
10:10. Okay, great. Thank you. I just can't hear well. Let's do a direction field for the differential equation dy dx is equal to, I think we've seen this one before, 0.2 xy. They must love that one. Okay? And that's in figure 213. Say again?
Yeah, 213.
Yeah. Okay? Now, let's us pick a few of these. I'm not going to draw them all, but let's do some. So let's say this is 1, 2, 3, 4, 5, 6, 7, negative 1, negative 2. You get the idea. 1, 2, 3, 4, blah, blah, blah. Negative 1, negative 2, blah, blah, blah. Okay? So let's pick some. I will volunteer to do where x is equal to 0. I'll do those for you, okay? Where x equals 0, this slope is 0, 0, 0. See, x is 0 every one of these points, right?
Yeah, but wait.
Second?
If x was 0, wouldn't the whole thing be 0?
Okay. At the one value where x equals 0, yeah. It's 0 everywhere. That's why I'm drawing 0 slope in here.
Why does the y change?
No matter what value you put in there, if x is equal to 0, the slope is 0. So you have a horizontal slope there. Okay, right? That's all that's saying. Okay? When y is equal to 0, you have a horizontal slope. So all these are, maybe I should I do that a different color? So it shows up better. Can you see I'm putting those in? Or I can put a different, huh?
It's a little tricky when you're doing the horizontal.
Okay, give me another color.
Let's do blue.
Blue.
Purple.
Okay. Okay. Does that show up a little better? So you know that at these points your slope is always 0. Okay, I've done the easy ones, okay? Now you can do any point that you choose. Now, earlier they had chosen, what was it? 2, 3, right? This is in a different example. So you chose 2, 3. So dy dx at the point 2, 3 would be 0.2 times 2 times 3, right? That would be 1.2, wouldn't it? That was what they got, wasn't it? Okay? So at 2, 3, it's 1.2. That slope is just a little bit greater than 1. Okay? So I'll put that as a slope. And you can pick every other point on the board, you know. Do a calculation and put the slope, you know, put the approximate slope in there. All right? You see what we're doing? Okay. And that's what you got.
Would
Now,
you add more values though? That would have like a line, I guess, to show?
yeah, I said, yeah, you can fill out every one of these. And then if you want to do the halves, you can do them here and here and here and here. You can do as many of them as you want to. And the more of them you do, the better your picture is going to be. Okay? But when you just do the hatch marks, like doing here, now they've got a little bit, much better scale than we do. Here's what it looks like. And again, you see all these horizontal ones on the x-axis and y-axis are horizontal. And then at the 2, 3, there's that slope there, just like I did. Okay, and that's what you got. Okay? Now, if you kind of connect the dots, the arrows, I'll say, you get slopes that look like the bottom part of this. Okay? And that would be curves that do something like, and this is going to be, you know, I'm not doing them well, okay? And yeah, you see, yeah, I've just sort of drawn them in. But that's what they got in the book. They put the blue ones above the line. At c equals 0, they've got this. They did it in red, so I'll go back and do mine in red too. This one would just be this line right here, okay? That would be that one, okay? And then the others deviate from that, curving less to begin with, and then more and more as you go on. Okay, my picture's pretty lousy. But you see, they just basically connected the arrows, okay? Now, but you do note when x is positive and y is negative, x positive, y negative, that would be down here, all these slopes are down. When x is positive, y is positive, all of them are up. When x is negative and y is positive, they're all down. And when X is negative and Y is negative, they're all up again. So sure, you get the general gist of this. Okay.
Is that the figure on 2.3, the directional field? See that one?
Say this again.
The direction field?
Yeah, the 2.3A is the direction field, and then 2.3B is where they've connected some of the
It
things
kind of looks
together.
like one of the electric fields.
What's that?
Electric field. Electric field?
Oh, electric fields. Okay. All right. They can look like this, especially if you had a charge up there and a charge down here. And these would be represented like charges because the field lines are bending away from each other. So that would be what this would look like, is that somewhere in the middle you have basically no charge because, let's see, that doesn't really go. No, I guess that's good. So in a sense, that could be an electric field. These are direction fields for this thing. I can't think of a circuit that would be an electric field for, but it could be. I'm not saying it can't. It would all depend on the magnitude of it. No, I don't know what it would depend on. But that could represent that in a sense, I would think. Or at least something fairly close to it. Okay. Now, if you remember back in Chapter 1, when we dealt with this very one, this is the first one we dealt with, when we did deal with it, we found a solution was 1/16 x to the fourth. And that's probably this one here. It's pretty flat in here and goes up really sharply there. Okay? But remember we said y is equal to 0 was also a solution. There it is. That solution is showing up right here too. But it's a whole family of solutions. Now, the key here is, what if you had some value you know is on that field, an initial condition? Once you get that value plugged in, like this one right here, that would be the field that goes like this. Okay? So that would be how you proceed from that. Okay? Is that enough on that one? Okay, let's move on to example 2. I think we'll use the same slide. Use a direction field to sketch an approximate solution curve for the initial value problem. dy dx is equal to sine y. Whoops, let me get back to black. Nope, it didn't take. Back to black. There we go. dy dx is equal to sine y. Okay? But they also give us an initial condition, y of 0 is equal to negative 3/2. Okay, we'll come back at the end and use that. So let's do an analysis of this one. Okay? Now, this time I'm going to choose my grid a little differently. I'm going to use, and it doesn't really matter that much here, but I'm going to do the same thing. Pi halves, pi, 3/2 pi, 2 pi, and so on. Pi halves, pi, 3/2 pi, and 2 pi, and so on. Minus pi halves, minus pi, minus 3/2 pi, and so on. Minus 2 pi. Minus pi halves, minus pi, minus 3/2 pi, and minus 2 pi, and so on. Okay? Now, notice the x, not going to matter at all. It's just what is your y doing. So basically, I'm just going to use the y scale here. Here is your x. Here's your y. And when y is equal to 0, you're at 0. And is that a minus? Or no, that's not minus. Yeah, okay. Y is equal to 0, 0. Y is equal to pi halves. Your value is going, and this is, now it's not on the scale. This is your slope. The slope is going to be 0. When y is equal to pi halves, the slope is 1. Oops, I better go. You want me back to purple again? Okay. That is 1. Here it's going to be 0. Here it's going to be negative 1. Here it's going to be 0. Oh, I didn't do those right, did I? I didn't do that one very well. I may have done those okay. Let me start over. Okay. The slope when y is 0 is going to be 0. So y is 0 everywhere along the x-axis. Okay? Now, the slope at y is equal to pi halves is going to be 1, right? Sine of pi halves is 1, right? You look like you don't believe me. Okay. Do you agree or not? Okay, yeah, you're easy. Okay, so that's going to be a slope here of 1. Everywhere that sine is pi halves. Okay? Even over here. Okay? Sine of pi is 0 again. Okay? Now, I'm going to put this 0 pointing the other way because I know what's happening here in between. Okay? And sine of 3/2 pi is negative 1. So the slope is going to be negative 1 here. Okay, and we can do this for the ones below and above everywhere else. These will be negative down here, 0 here, one way or another, positive here, 0 here. You know, they keep on trucking negative here, and you just keep on going all these. Okay, now what that does for you is mean that your curves in here, and let me put these in different colors because the book does. Let's do one sort of that color. It's doing something like that. And this one's doing something like that. And this one's doing something like that. And this one's doing something like that. Where, and here, they're coming down like this, because the slope is negative in there. Whoops, that was an ugly one. Okay? They need to be following the contour, okay? And then they reverse and go back like this again. Okay, so every time in between every 1/2 pi, they flip directions. These are coming down, these are going up. These are coming down, going, whoops. I did those up there backwards, didn't I? Okay, but you get the general idea, okay? Now, they did it in the book. Okay, now, let's then, our initial condition, when x is equal to 0, y is equal to negative 3/2. Okay? X equals 0, y is negative 3/2. That's down here. So it has to go through that point right there. Okay? Well, I can see my curve. See this one? I'm going to keep it in red now, is going to be going down like this. All along here, these are going like this. All down here, I've got the arrows going the wrong way. They're going like this. There's zero slope. It doesn't matter. Zero slope. So this is the curve that is a part of. Okay? That's heading in this direction. The slope is negative here. So that's the one. No, how did they have it backwards? Oh, wait. When x is 0, I put it in the wrong place. It should be right here. When x is 0, y is negative 1/2. Yeah, I put that in the right place. But the curve at minus pi halves, sine is a negative 1. So it seems like this curve should be pointing in this direction. The book has it pointing upward. No, it doesn't. I'm looking at the wrong graph. Goodness gracious. No, I am looking at it. They have it over here. And I don't buy that. Maybe that's a different curve. Let's see. Oh, they don't show this one. Sorry. No, they say that's example 2. Show this, but it looks like to me the field should be going in this direction. Negative 1/2. Oh! Dumb. I've been throwing my negatives wrong. Negative 1/2 is in that direction. Sorry about that. I turned it going the wrong way. So they're right. It's going like this. Okay. Okay. They're absolutely right. Mine was wrong. I don't know where I got that from. Okay. Okay. These arrows are pointed wrong. These should all be all along there. You're at negative 1, including there. Okay. Sorry about that. So all mine are sort of backwards there. So up here they're going up, down here they're going down. Okay. Got it. Okay. Interpretation of the derivative as a function that gives a slope plays a key role in the construction of the direction field. And remember now, your arrows always are pointing up or down, but always pointing left to right, never right to left. So how I got turned around there. Okay. Now, they have in the remarks here something called the method of isoclines. Here they're talking about what you use isoclines for are areas of equal elevation. Have you ever seen a topographic map?
Is that like a mountain thing?
Yeah, it could be used to describe mountains. Watersheds. You're interested in topographic maps because that shows lines of equal elevation. So if you're up here, anything down here, the water's got to flow downhill. And you get the whole watershed there. You're using topographic maps. Those are called isoclines. Well, obviously they use that for more things than elevation. But think about a weather map. You'll see there they have isobars, equal barometric pressures. And then you have high pressure systems or low pressure systems surrounded by that. Yeah, exactly. But on that, until you read the numbers, you don't know if that circle means it's a pit or if it's a mountain. You just have to see which way the numbers are going. Okay? So that's exactly what we're talking about. Isoclines is equal elevation. Isobars would be equal barometric pressures. You could have I can't think what equal velocities. If you did wind velocities, you know, you could have iso whatever those are. And that's exactly what you're doing here. You're sort of connecting the dots, and that gives you the isoclines. Okay. Now, 2.1.2. We have just enough time to get started in that, I think. I believe I'm going to go back to my, let's see, let me do it easier. There, this page. All right. Autonomous first-order differential equations. Way back in section 1.1, we divided the class of ordinary differential equations into two types, linear, nonlinear. Okay? We now consider briefly another kind of classifications of ordinary differential equations, a classification that is of particular importance in the qualitative investigation of differential equations. Remember, at the end of the chapter, we said there were analytic, which we haven't gotten to yet, qualitative, and then numerical. This would fit in the qualitative, okay? A classification that is of particular importance for the qualitative investigation, okay? Ordinary differential equation in which the independent variable does not appear explicitly is said to be autonomous. For instance, let me get my pen back. There we go. dy dx, what we were just talking about was some function of x and y. Okay? Pick an x and a y and you get the slope at that point. Okay? Now we're going to do something different. We're not going to have the independent variable in the picture at all. It's just going to be some function of y. Okay? And now it says we shall assume. Now, if you think back at some of our models, the population model, the next 2 or 3 models, we were running into this every time. We didn't call it that then, but we were running into it. The rate of change of a population depends on the size of the population. Not on time at all, on the size of the population. Okay? So this is when the only functional dependence here is on the dependent variable. An ordinary differential equation in which the independent variable does not appear explicitly is said to be autonomous. If the symbol x denotes the independent variable, then the autonomous first-order differential equation can be written as, now you write this the other way, and I wish they'd have done the capital. I've got a sneeze, sorry. Y'all awake yet?
Yeah.
Okay, those poor people at home, they didn't know that was coming.
Whoever's got headphones is going to go dead.
What's that?
Whoever's got headphones is going to go dead.
Oh, yeah. Blew out the eardrums. Okay. It seems like to me their illustration here should have read f of y prime is equal to 0. Always before they made that the capital F, here they made it little f. I don't think that should have been the case. I think they should have put it capital. In other words, there's no independent variable dependence here on the differential equation. Now, we'll assume throughout that the function f in this equation here, okay, that's equation 2 here, and its derivative, f prime, are continuous functions on y on some interval I. Okay? So let's look at a few of these. Here's one. dy, dt, no, they're doing dx. Okay. dx is equal to 1 plus y squared. Okay? Now, hint. It's not a linear differential equation, okay? Even though, oh no, this is just saying first order differential equation. That is first order. It's not linear because the y is squared. But this is autonomous because there's no x that shows up here at all. No dependence on x, okay? You're taking the derivative with respect to x, but not there. How about this one? dy dx, you may have seen this one before, is equal to 0.2 xy. Is that autonomous? Help me. Is that autonomous?
Sure.
No, it depends on x. You see an x in there, don't you? This is autonomous, this one's not. This one has no x here, this one does. We're going to look in this subsection only at autonomous, okay? Now, if you go back to 1.3, which is what I was saying, and think back on there, dA dt is equal to Ka. How many things did we see like that? We saw radioactive decay, we saw the population growth, we saw virus spreading, we saw lots of things that look just like this. Autonomous equations. No independent variable, in this case t dependence. Okay? Here was another one. Dx dt is equal to kx times n plus 1 minus x. Okay? That, if you recall, was our disease spread. Okay? Notice the t doesn't show up in there anywhere. It's not a time dependence, it's an exposure dependence. Okay? That's all. Okay? This, I think, was Newton's law of cooling. dt, capital T being temperature, lowercase t equal time. That would be K times the difference between T and T ambient. But they called it M, which is, what did they use that M to stand for?
I think it was like
The medium. That's it. Second?
I think it was like the temperature goes to or something.
They said the medium's temperature. In other words, the air in the room. Okay? So, which I call ambient temperature. That to me is a better phrase. That's how I've always learned it. Okay? Again, no time dependence there, only temperature dependence. That's an autonomous equation. Okay? Remember when we were doing the salt solution, we had dA dt is equal to 6 minus 1 over 100 A. That's what it came out being with the things we were given. That's autonomous. There's no time dependence there. It's all amount dependent, the salt content. That was your differential equation. Yeah, you're taking the derivative with respect to time, but it doesn't show up. Now, with this kind of equation in mind, let's consider, now this sounds like Cal 1 again, and in many ways it sort of is, the zeros of a function f, any of these functions f that we have here, okay, little f, okay, are of particular importance, special importance. We say that the real number c is a critical point of the autonomous differential equation if it is a zero of that equation. Okay? So, a equals 0, that would be 1. This one doesn't have a critical point, does it? Because this equation doesn't have a 0. Okay? This is always positive. Okay? This would have a 0 where x equals 0 or where x equals n plus 1. Right? Okay? This one is not autonomous anyway. This one would have a 0 at, set that equal to 0, so a equals 600. That would be a 0. Okay? That one up there would be a 0 when t is equal to t of the median. Okay? Those would be your zeros. Those would be your critical values for those various differential equations. Okay? Now, a critical point is also called an equilibrium point or a stationary point. You could call them any of those things. You could call it Fred if you wanted to. I don't care. Okay, now observe that if we substitute the constant function into that, then both sides are 0. That means if C is a critical point of the equation, then y is equal to C is a constant solution of that differential equation. Okay? Yay. Okay. A constant solution, y is equal to C, is called an equilibrium solution, and equilibria are the only constant solutions of that. Boy, that's quite a statement there. Now, do we have time for example 3? I think not. So let's pick up and go with example 3 next time. Okay? Oh, Daniel, you came in after I did this. Do you want to go on and get a copy of the first test? Okay. And you'll need to listen to the recording about what you need to do. You've got to show all your work. But before you do that test, I know you know what test you got to do first, right?
Yes.
Every one of them, right? And what, both courses was it? Yeah. Okay. Got to have them. Okay. At some point, you know, somewhere like 6 or 8 weeks into the term, some point, and we're already at week 2 or 3, that I changes to an L. So get them in. Okay, good deal. Shouldn't have recorded that last part. Take care, have a good weekend. I don't know if the Cal 3 has uploaded. I imagine it has. I'm going to try to get it.
I haven't had time this week to go back to the lecture.
Oh boy, are you flunking badly. Okay. Okay.
Good.
Yeah, you're all right. Yeah.
Let's see. I think I have 2. Let's see. You did the first one last Wednesday, right?
What's that?
You did the first Cal 3 class last Wednesday.
Let me see. I've got it in here.
Like you did the syllabus last Wednesday, right?
Well, I did the syllabus, but that wasn't all we did.
Well, you did chapter.
Yeah, here we are. Okay. You showed up the first class, but didn't do anything. We had class the 29th, real class. We went over syllabus, safety, research paper, all that stuff, and got started in the actual class.
You did the sphere.
And then we did on June 3rd and yesterday. So we've had syllabus class with a little bit and 2 full classes.
Okay, so I got 2 videos to watch, basically.
You might want to watch the end of that.
Oh, I did watch the 3rd one.
Okay.
I took all the notes. You did the sphere. The equation for the sphere.
Yeah, okay.
Yeah.
Okay.
Yeah, it's like
AX plus BX plus, or AX plus BY plus CZ plus D.
Something like that, only they have squares on it for a sphere.
Yeah.
Any curve has squares. Okay, good deal.
All right. Are you you made it to cross product yet?
What's that?
Cross product?
Let's see, I'm trying to, we did some, okay, we're in chapter 12 now, and we have been using the cross product. We didn't go over it. You should have had that earlier, I think.
The cross, talking about where you did
The matrix IJK, right?
Yeah. All right. Sounds
Yeah.
good.
Yeah.
See you.